Good evening, everyone. Welcome to today's problem solving section, course Digital Design with Verilog, week 4. So, in the last class, we have seen the Kuhn-McCluskey method for minimization of the logic expression. So, we observed like K-map, we can use it for minimization for up to like 6 variables, but like up to 4 variables it was fine. With that, with 5 we had little, the complexity increases, until 6 we were able to minimize it. For the more number of variables, the other methods like Kuhn-McCluskey method can be used. And here if we observe, the first step was to, if we have this as the minterms, the first step was to count the number of ones. So like if 0 is there, if we consider 4 bits w, x, y and z, so first we have to write the 0 number of ones, and then this consists of 1 number of ones. So we have 1, we have 2 and 8. So in this way, here we have 2 number of ones, and the number of 1 here is 2 and the number of 1 here is 3, whereas here the number of 1 is 4 and here the number of 1 is 0. Next we wanted to form a group, so the grouping was with respect to this and this complete batch, and similarly like this with this, and we were comparing with this to find if there is a 1 bit difference. So all 0 will have a 1 bit difference with all the 1, 2 and 8. So we have 3 groups, 0, 1, 0, 2, 0, 8, and similarly class and similarly we will have a 1 bit difference between this. So like if we consider 0, 1, 0, 2, 0, 3, 1 bit difference, and wherever we have a difference, like here we have 1 bit difference, we will put a we will mark that place with a dash, and whichever is terms are covered we will put a tick marks. So the uncovered terms we have to consider at the end. And similarly now again we will try to form a group with this 2 and with this 2 and this with this 2. So the next step grouping should be wherever the dash is there, it should be in the same place and 1 bit difference. So this and this. So we can combine 0, 1, 8, 9, and wherever this terms we have combined, we will put a tick mark. Then next we have obtained this. Now we have to find what are the essential prime implicants. So we will plot a essential prime implicant chart, and the minterms are obtained from here. So if we have this, the equivalent minterm is x bar, y bar, and for this the minterm is x z. So with this minterms, if we observe like for this particular 2 is only grouped by this minterm, and similarly for this by D. So the minterm B and D are the essential prime implicants, and then the leftover, like the other terms which we need to cover are 1 and 9. 1 is covered by E and 9 is also covered by E. Yes, other minterms are covered already, and 1 is also covered by C. So the final minimized expression will be the essential minterms, we have to keep it, and A or we can have B plus D plus C. So we have two possible expressions. So next, how to select the non-essential prime implicants. So here we have kept the min terms with three number of variables like literals, and here the number of literals are like 4 and is 4. So we sort according to the number of literals, and so if we observe that uh, we need to select the minimum number of prime implicants for the if we have the min terms which are not covered by A and C. So if we consider A and C has the essential prime implicant, then the variable this covers A covers like 13, 15, 29 and 31, and similarly C covers the 3, 7, 19 and 27. So with this we have the like we have to select a minimum number of prime implicants that from this B, D, E, F, G, H, I, which will cover this min term which are left over 0, 1, 4 and 20 as well as 22. So can we automate this process? So here we saw the leftover like min term, we had options of A, either A or D. So can we automate this? And to that, can we reduce this prime implicant chart? To reduce the chart, if you observe from this, we will remove this A and C, and also if any other redundant terms are there. For example, B is covering this, which is already covered by C, and this is covered already by A. This is also covered by C, and this is covered by A. So B we can remove it. The next is D, E, F, G, H, I. So from this, and what are the uh, min terms left? 0, 1, 0, 1, 4, 20 and 22. So we have listed them. Now from this, can we further reduce it? So we can reduce the row as well as the column. So now we have reduced like this number of rows, and this is we have reduced with respect to the dominate, like B is covered only terms which are already covered by A and C, and the reduced chart results after the removal of the rows from the A, B and C, and all the columns covered by them shown in the figures. Okay. So next, the now the what are the possible P we have to select from this? Can we write it as a product term? So how we obtain this expression is H for 0 we can choose between H and H or I. For 1, what are the product terms we need? Either G or I. And similarly for this one, F or H. And for this one, E or F. This should be and because all of the min term has to be covered. For 22 it is D or A. So if we observe, we obtain this expression like this: H or I and G or I, F or H, E or F, D or D. Now we have to simplify to get the minimized expression. How we get is like multiplying. For example, if you multiply this with this, GH plus GI plus I, and again if we take the common GH plus I multiplied with the next term F plus H, so and similarly we obtain this expression. Okay, so for P at least 3 rows are needed to cover the reduced chart, and for example either this 3 or this 3, and this has 4, so total 1 2 3 4 combinations, and this we will not take, this is not a minimized expressions. So what are the possible expression? It is A plus C, which is like we said essential, then E plus H plus I, or it can be A C D F I, or it can be A C E G H. So now we were reducing the number of rows. So let's just see this example. A row of a prime implicant chart is said to dominate another row V of that chart if U covers every column of the V. So if row U dominates row V and the prime implicant corresponding to row U does not have more letters than the prime implicant corresponding to row V, so we can delete the V. If we consider in this example, essential prime implicants are A, B, J, K. So essential prime implicants are A, B, J and K. So if we see C, D, from this we will obtain the reduced implication chart by removing A, B, J and K. So we will have C, D, E, F till I. Now from this we are getting the final chart, like reducing the number of, like this if we observe, F is covering only 10 and 11, whereas E is covering 10, 11 and 26. So E is dominating over F, so we will keep E and delete the F. Similarly, G is dominating the H and I, so we will remove this and keep E, G, whereas C is dominating over B, so C we will keep. So this is the final chart we obtain. So from this, again the essential are C and D. G is already covered by this, and this is also already covered. So G is not needed. So again these two are the essential, and this is essential from the first chart. So we observe this is the minimized expression. So in this way, by deleting the rows, we are able to minimize the expression. Now can we delete the columns? So in the columns, if we observe 11th column, this min term is grouped by E, F, G, I. So it is dominating to the 10. So we can delete this and keep this. It is opposite to the deleting of the row. So if we read The column I in the prime implicant chart is dominating 2j. So here uh, 11 is dominating over 10, and whichever row is column is dominating, we will delete that column. So here the expression which contains only the dominated I. So if I dominates j, then I is deleted from the chart. So we will remove this I, that is 11th. So next, if we don't have any essential prime implicants, so we are not able to reduce the chart further. That means we don't have any dominating rows or columns and also no essential prime implicants. Then we will go to the branching. We have obtained this min terms from this cyclic map. So in the cyclic map, we can either group it like this or group it like this. So because of this, it's like every min term is covered by two of the product terms. So we don't have any essential prime implicant as well as no dominating row, because every row has two, and for every column also two. So we are not able to further reduce this. For this we will go for branching. So what is branching? Branching, we will, for example, choose first one, that is we keep A is say essential. When A is essential, then we can remove this and this. So from 5 to 15 we need the minterms to be covered, and from B to H, so B to H. Now C is dominating over B, we can remove B. And row C and G must be selected. So next we have A, and then now the essential is C, because this is covered only by C. If C is essential, if we remove this C and remove this, we observe G is essential, and similarly E is essential. So in this way, branching, we can reduce the uh, chart, prime implicant chart, even when there is no branching, or when there is no common rows or columns, we are not able to delete the rows, dominating rows or columns, and also no prime essential prime implicant. Okay, so in general, it is now again here we can have another way of expression. So instead of starting from, we consider A as the essential prime implicant. Instead of A, we can consider H as the prime implicant, essential prime implicant, and similarly we can proceed. When we consider H, then H should remove 0 and 8, and then we have to proceed further. Okay, so here, so with H as starting and A, so we obtain two possible reduction. Okay, so next is two-level logic optimization. So we find that prime implicant, so we have some optimal methods which we have already seen are the Karna map method, and the second method is from the Queen-McCluskey method. So this always gives the minimized expression. The second method, which is the heuristic based method, which we will see next, is espresso. So this takes less time and gives a near minimal expression. So next, what are the problems with the optimal methods that we are going for an heuristic method is that, and also here for the heuristic method, if you increase the amount of time for generating the solution, it will give better solution. So the main reason is because of the exponentially large prime implicants. So the number of prime implicants can be exponentially large, and then forming this chart and finding will be time consuming process. So heuristic based method is also for a two level circuit minimization. Okay, so here in this method, if we have start from here, we find some minima, so we say this is a minimum solution. So again, if you want, we stop it and restart from some other point and we reach it. It may be a global minima, or if we could have started from here, again a local minima. So what is the procedure? We start with the min term and we try to expand it. If we find any irredundant terms, like we reduce it, expand it. So we will see this with the example. So we try to expand the cube in F. Okay, so this is expand. Okay, from here, if we have this, we start with 1, just a group of 1. Then we try to expand it to form a group of 2, and if possible, we will try for expanding into and forming a group of 2. So everything will start by forming a group of 1. Next, if we expand, say we have this point, which is that 0 0 0, where 1 is there, and we start expanding in the y direction. Right direction in the y direction, we get x bar, z bar. That is, in the y direction we have expanded like this and we got x bar, y bar. And similarly, if the same point we expand it in the z direction, we get x bar, y bar. Again we will z direction is this one. This is the x direction. So what is the min term? 0 0 0 0 1 0. So it is y z bar, and in the z direction it is this one. So again, if you expand in the x direction, we obtain y bar, which is the group of 4. Again here, x direction, we get a group of 4, which is again y bar. So But if we started from this point and expanded in y, we could have got this as the prime implicant, whereas if we had started from z or x direction, we could have got a minimized expression for the as the prime implicant. So next is irredundant. So example, if we have this term, we observe this is covered already by this group and this group, so it is an irredundant which can be removed. And reduce, we if we want to again start, like for example we started and formed x bar z bar, we can again reduce it and come to all zeros, and from here again expand in z or x direction, so that try whether we can get a more minimized expression. So if we have this as the term, now if we want to reduce this, we take this point and group and we reduce it, and then now we expand it, instead of in this direction we expand in this direction. When expanding in this direction, we observe this is an irredundant term, we can remove it, so we have removed it. Here we had 4 product terms, but here we have only 3 product terms. So in this way we can get further reduced expression. So okay, any doubts still here? So writing this as an algorithm, we have this offset and on uh, onset is for the like min terms wherever it is 1 in the k map if we see, and offset is wherever it is 0, and dc set is when we have don't care. And so whenever we expand it in one direction, we find any redundant terms, we remove the redundant cubes, and after that we in the loop we reduce it further, expand in another direction. If we find any redundant cube, we remove them. Like redundancy, we remove in the irredundant step, and until we are not able to get further improvement. And at the end, we have 3 more steps: reduce grasp, expand grasp, and again the same irredundant. So we will see what is this reduce grasp and expand grasp. So reduce for each cube f, so we will add those subcubes that are not covered by any other cube, and expand, we will expand the subcube and add them if they cover another group. So for example, if this is one group, so this is already covered by 2 groups, like this one and this one are already covered by 2 groups, so we will not consider. These are only covered by one group, so such groups we have considered. And now we will try to like form expand, so we can expand it like this, and we can expand it like this, so we further reduce it, like then we will observe that this is redundant, that is redundant group in the irredundant step, and we can remove this, this and this x, and we get the minimized. So this at like any time algorithm means if we have a lesser time we will get a lesser accurate solution, lesser like as the time is increasing we will get a minimized expression, and algorithm successively generates a new cover until no further improvement is possible, and this is gives a near optimal solution. So it takes lesser time on high speed, like less than 15 minutes to generate the output. Okay, so till now whatever methods we have seen, like the K map or the twin Kluski method, they are for the two level logic. Now we will see what is this two level logic, minimization and the multi logic, and the techniques for both. So two level versus multi level logic. So if we consider f is equal to uv xz plus wxz plus u bar y bar z plus v bar x bar z bar. So if we try to draw the logic implementation, it is u v x z w x z u bar y bar z v bar y z bar, and these are connected to a OR gate to give an F. So this is level 1 and this is level 2. So if we further like apply the process called factoring and say we take xz common, then we get uv plus w plus u bar y bar z plus again v bar z bar. If we take common we get x bar plus y bar. Can we take z common? So we obtain this expression with into x bar plus y. So now if we draw the logic diagram for f is equal to z for this expression that we obtained after applying factoring steps. So we have the f as this expression so we have uv and or with w and with x, then we have to perform an OR with u bar y bar. Further this expression. So here if we see the number of level is 1, 2, 3, 4, 5 and 6. Level is 6 and literal count is 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And this is called as multi-level circuit. So with multi-level circuit, sometimes it gives better circuit. So next, logic optimization for multi-level outputs. If we have two outputs for the same circuit, F1 and F2, we observe that UV plus W is common for both F1 and F2. So we can compute UV plus W and share this for both F1 and F2. So this is F1 and F2. So UV plus W is shared between the F1 and F2 outputs. Similarly, why we need a multi-level optimization? So like if we consider this optimization like this parity check, we for the two level we have 32 literals. Why? For every one 8 literals, 8 into 4, so total 32 literals. Can we reduce this further? And what is this parity? Like if we have say odd parity, say 0011, 1011. To example, if this is if the parity say is we want to make this even, then this is 0, making this even 1. So the input is A, B, C, D and the output is the parity bit, parity check bit. And similarly, like if we say this is, and when we say check, this is not an odd parity and this is an odd parity. Okay, so how can we reduce this, optimize this? And so what are the advantages of multi-level logic? It requires lesser area and delay compared to the two-level realization, and it is difficult to obtain the optimal multi-level realization because of the much larger design space exploration. So we will be in this class seeing the independent synthesis, which is not dependent on the synthesis. So for the multi-level logic optimization, we will be using the algebraic method. So in the algebraic method, this one a plus bc equal to ab plus c into a. This is valid in the Boolean expression and not in the algebraic expression. And also complement does not exist. So x plus x bar, this is not in the. This is not equal to 1. Here it is like simply a plus b only. Okay, so with this expressions, we have a method of division. In the division, we have a divisor q, we have a quotient, we have a remainder, and we have a dividend. So if we have this f is equal to AC plus AD plus BC plus, if we take A plus B common and C is the common, and again here A plus B, D is common, so it is C plus D plus E. So E is the remainder, this is the quotient, and this is the divisor. I hope how you understand like how we got A. Now again C plus D is common, A plus B is plus E. This is how we got that expression. So in the algebraic method, we saw we will have a cube, we will have a D. This D, which is a cube free, like this is a single cube. I mean it is a product term. This is also called as co-kernel, and this cube, which is a quotient, which should be the cube free, we have a remainder. This is called as a kernel. Okay. So if we have an example, say f1 is equal to CE plus DE, it is E common C plus D. So this is quotient, this is the divisor, plus the remainder is 0. Say f2 is equal to AC plus AD plus BC plus. So this we have seen that we will get AB, CD. So here we have C plus D term, which is common term. So we can rewrite these expressions. Yeah. So we have seen CD is common in both the places. So we can name this as, we can compute this CD and store it in F3, and like not like storing, in the sense we can reuse it. How we have reused it here. This UV plus W, we have reused it. In a similar way, here F3 we can reuse it. So here we will have F1 is E F3 and F2 is F3 A plus B plus E. Okay. Okay. So with this, we have seen what is the Q or like Q and D. Say for example, here we have a kernel K and a co-kernel C. So A, B, C can be a product term, A, D can be a product term, E, F, G. So these are called co-kernels. And what is a kernel? This there is no common term, so it is a kernel. Similarly, so these are the examples of a kernel. So here we observe there are no common terms. So what is cube free? There are no common terms. This is not cube free because we have xy plus xz, we can have a common as x. Similarly, this is cube free. This is also cube free. Here we have common xy plus w. Okay, so no common terms. Okay, so kernel is a cube free. So the sum of the examples include okay, so here now algebraic methods. This is the expression. In this expression, we are having co-kernel, means we are dividing it with WZ. This F and whatever we got is U plus V. The other will be remainder. Why? If you take WZ common, you can take from here, here. So it is U plus V. So if we write this, we have a W expression divided by Wx Wz. So F is equal to UWZ plus UXZ VWZ VXZ YZ plus UV. So if we divide, the common term will be WZ, U plus V, and the other terms will be the remainder. So now if we divide it with U, V, we will get UZ W plus X. This is remainder, this is quotient, this is divisor. Here there are like no other sub expression, so this belongs to level 0. Now if we take as U, divide the expression say with U, so we will get wz plus xz plus v, and the remainder, the other three terms. So this will give z w plus x plus v. This is a level 0, so this complete becomes a level 1 kernel. Similarly, if we divide by 1, it is the entire expression. If you take q common, this is a level 1, so this complete thing becomes level 2 kernel. Okay. So any doubts still here? So next, according to this theorem, we will see like why the kernels are important. Say if we have two functions f and g, and then this like we want to identify the common sub expression. So then this common sub expression will be the intersection. So if the like we identify the kernels of for the function f and g, and then say k is the kernel of f, we take the intersection. If they have a common any common sub intersection, then that intersection of the kernel we will be able to find the common terms. So we take the intersection, and that is the SOP form with the common cubes. So let's go directly to some questions. Like example, yeah. So the procedure, the algorithmic method, the algebraic method, f is equal to, we get a cube 1 which is multiplied with the kernel 1 plus remainder 1. So this is a product term and this is a subterm, sub expression, and this remainder. So we get WZ. So if we have an expression like this term we consider as remainder, and this is the kernel 1 and this is the cube 1. So if we have say xy plus z plus w plus uv plus remainder, we call this as x plus y plus this term as stuff 1 plus remainder. Okay. And similarly if we have the same thing xy plus z plus some other expression wv plus x plus remainder, we call this as x y and this has again stuff 2 and remainder. So the intersection is the x plus y term. Let us see some example. Because here inside the kernels we observe that we see x plus y is the common term. Common term we can say, or is the intersection term. Now if we have f and g, two outputs, two output of function, so we will have a kernel for f and kernel for g, and with co-kernels the dividend, like this is the co-kernel, and we observe that if we take this two, AB is common if we take the intersection. Now how we obtain this? In the f expression, if we take E common, we get A plus B plus CD plus the remainder is AB. And between these two, the intersection, again here it is E common, A plus B. Okay. The other terms will be the remainder. If we take the intersection of these two, we have A plus B. But if we take intersection of BC plus DE, it is null. And now we will see in that way. Say BC, this is B plus C, we have to take intersection of D plus E, which we saw it is null. And if we take intersection of AB plus A plus B plus CD, A plus B, it is A plus B, and this is the stuff term. So how this common term will be helpful in this expression? F can be rewritten as E, A plus B, we have seen the common term. So in the multi-level logic, first we can compute A plus B and share that output with the expression of G. So here this is the expression with the common expression of A plus B. Now the question is like, how can we identify the kernels of a function? So yeah, in multi-level logic minimization, if UV plus W is the common sub expression, we can first compute that and then use that F3 in the expressions. So now if we divide by 1, we will get the complete expression, and in here no cube B has again B is a factor. Here this B, if we divide by B, this is a there is no common term in this, so it is a kernel. Again this is a kernel. So next, so till now, like for identifying the kernels, we have used the brute force based approach, and which is not efficient. So can we automate that? So rectangle covering to identify all the kernels. So for that, if we take this expression, so there are total 4 cubes. We write all the 4 cubes. How many distinct literals? We have total 6 literals. So in this way, here we write the literals and cubes. Next, we have to form the rectangles and then group the rectangles. So if we take UZ, we form a rectangle with UWZ and UXZ. So this is a rectangle of 2 cross 2 size, and this is the maximum possible. So this is called a prime. Similarly, we can have a rectangle by forming a group of with UWZ, UXZ, UV. So this forms 3 cross 1, and this is also prime. So if you want to take a non-prime example, just this U can be grouped with UWZ, UXZ, which forms 2 cross 1, and bigger one can be grouped. So this is not prime. And in the next rectangle covering problem, if we take UZ and UWZ, UXZ, so they are one. This forms a rectangle. So this is a prime rectangle. So what is the rectangle? U W Z U X Z. So what is the co-rectangle? It is the term excluding U and Z. So with we have v, w, x and y. Similarly, I will change the color. If we take u, z, this will give u, z. So this is a co-kernel, and in this u, w, z plus u, x, z, if we keep the variables v, w, x, y and remove u and z, we will get x plus w. This is the kernel. So in this way we can identify the kernel. Next, yeah, so here if this is the kernel, we have to, from this expression we can get what is the kernel by removing, keeping these terms and removing the terms of uz, and this uz is the co-kernel. So we have seen how to find the kernel. Next is if we have say kernel, we have kernel of f and kernel of g, x plus w and say this consists of these terms. So we can rewrite this for the kernel of f with the terms like new kernel ax w aw plus axz ay plus say the other the terms from this, say axy az plus aw av. So this is written like the sum of the product expression. So this is the f1 expression, f2 expression, and here we are taking the u z common. So we got w plus x and this terms. So similarly, now to get the kernel, we will write this as aw ax and this one is another. So finally if we get as this term and this term. Okay. So from this kernel cube incidence matrix, we have aw ax. So the from this if we take this forms a triangle which is a prime triangle, prime rectangle, and so with this we get w plus x. So we have w plus x as the common. So So F3, we take WZ. F1 can be rewritten as F3 U plus and F2 can be written as, so in this way this can be shared between F1 and F2. So again here, so we can get a prime rectangle by taking UWZ, UXZ, which is a UZ prime rectangle. And also we can get, like, we take YZ, WYZ, then this forms a prime rectangle which is YZ. So we can first compute YZ and then with respect to that F1 and F2. So with this we will solve some of the previous year questions. Which of the following statement is correct for Q-Minkowski method for minimizing switching functions? S1, group the minterms having the same number of ones. S2, group the minterms having the Hamming distance 1. So what is the answer? Yes, S1 is the correct answer. So we have to group the minterms having the same number of ones. Next question. For which of the prime implicant chart, which of the following statement is correct? Column M is dominating column N if M has minterm in each row in which N has minterm. A row M of a prime implicant chart is said to dominate another row N of that chart in M covers every column covered by N. So what is the answer? Answer is S1 and S2. Yes, because a column M is said to dominate column N of if M has minterms in every row where N has a minterm, as now M acts as a cover of N. Okay, next. Which of the following is not for the two-level logic minimization? So we saw K-map, Q-Maclensky method, gives the optimal solution. And Espresso, this is a heuristic based method, so gives a near approximate solution, and all these are for two level logic minimization. So for the multi-log, we use the algebraic method. Okay, so going to the next question. Why is the prime implicant chart method to minimize switching functions computationally expensive? Because we said that the prime implicant grows exponentially. Like the number of prime implicants can be exponentially large. And prime implicant is dependent on K-map grouping. No? The number of product terms cannot be reduced by the prime implicant chart. We can reduce it, but computationally it takes large time. All essential prime implicants are not covered by the prime implicant chart. This is also not true. Going to the next question. In the expand process under the espresso technique, any implicant is expanded until it forms a prime implicant. So this is also true. Then branching method is applicable when the prime implicant chart has no essential prime implicants, no dominating rows and no dominating columns, so that when we perform branching, like we select one, like A or H, we first take A and further produce, we get a minimized expression, or we go through the next branching, that is H. So all of the above. So next question, for the switching function, how many minimum possible expressions? So if we are using the Q-Maclensky based method and start the grouping, the step 1, say 0 number of ones, and we have V, W, X, Y and Z, and 1 and 4 have one number of 1, and next 3, 20 has 2 number of 1s, 17, 13, 19, 22 have 3 number of 1s, we have 17 in the expression. I think this is not 17, this is 7. And 15, 23, 29 have 4 ones, and next we have 31 which has 5 ones. So this is our step 1. Next, going to step 2. So we have to group between this, the next group, like the below group. So we get, say, the V, W, X, Y, Z, say 0, 1, because 0 can group with all the both the numbers 0, 1 and 0, 4. So one bit change, we will mark it with the symbol dash. And the next group. So the next group, I will write it here, 22, 23, 15, 31, 23, 31, 29, 31. So this was the iteration 1, so step 1. This is for the step 2. And next step 3. Three, 19, 17, 23, we can form a group. So we have covered 3, 19, 17, 23, and then 17, 23, 15, 31, and next 17, 15, 23, 31, and next group 13, 15, 29, 31. So this is so this covers 13, 15, 29, 31, these are also covered. Seventeen, 15, 17, 23, 13, 15. This is remaining. 1, 2, 3, 4, 5 and 6 terms which are remaining. So from this, if you start writing, this will be W bar Y Z, X Y Z. This is also X Y Z. This is W X Z, and this one V W bar X Y, and this one V W bar X Z bar, and this one V bar, W bar, A, Y, Z. This will be V bar, W bar, X bar, Y bar. $317. Anywhere we have covered. 317 is already covered, so this is also covered. This term is not needed. And this is V bar, W bar, X bar. Okay. So these are the 6 terms from the slides. We get this, and these are the min terms given in the question. So now to reduce this, essential terms are AC. B is already covered, so we remove all these 3 and we are left with D, E, F, G, H, I. And from this reduced chart, we have this expression, and after simplifying we obtain this expression, and we observe we have 4 possible. Seven also have, okay, sorry, yeah, this 7. This 7. 7 also have 3 first term. Yes, this is present, so we can remove it. So we have total 4. So is this question clear? Any doubts? So going to the next question. What is the objective in the algebraic model of multi-level logic minimization? We have to find the common sub-expression. Okay. So going to the next question. Which of the following switching function is not a kernel? Kernel means there should be common sub-expression. In this, there is no common sub-expression, so it is a kernel. And again here also, so it is a kernel. Here we have x as a sub-expression, so we get this. So this is not a kernel. Okay, so till here, any doubts? So from next week we will start Verilog. So till here, like, any doubts? Today I will just give some like basic syntax. So in Verilog, we want to write, like we write any code to synthesize it to the logic, like we can have a gate level, we synthesize to gate level circuit. So we have codes which are just for testing, which is used for testing purpose, and we call them as test bench. And the code which we write for the logic is, we start with the module and we define the input and the output port. Say A is an input, B is an output, and every module is end with an end module, and we have various types of modeling like behavioral, and we will discuss that next week. So first, if I want to say assign this is A, this is B, because A is the input port. Also we have in-out port also. This is the output port. And another, like for example, if I want to define this in this way, A, B, here this intermediate, we want define a variable called wire, because we are not storing it anywhere, so just as a wire, and say T. So if you want to write a Verilog code for this, we need to define this wire, which is T. Similar to C, every line we will end with a semicolon, and say we are using a gate level, so we are calling a NOT gate, and the gate name, say G1, output followed by input, so T, A, again NOT G2, output followed by input. So the next method can be like, I have a wire T and I use the NOT expression, this complement directly. That means we have to assign the output T to NOT of A, and then assign B as these are single bit, so both can be used. So next class, like we will see which is the bit level operator and the logic operator. So, and then every module should end with the end module. Okay, so similar to this, if we want this value to be stored, say some flip-flop, so here comes the keyword register, and this things we will see later. Yeah. So now if we want to test this, that means we want to apply some input patterns. So our module is a test bench. inputs we need to store it. So we have to define as a register A, and outputs we are just observing, so B, and we have to call this module. Okay, so here one small correction. Module will start with the module name, say gate. This is also module. So module should always start with a module name, import list, input and output port, or here we can also like directly give module gate A comma B, then define what is input, what is output, and the operation, then the end module. This syntax is also a valid syntax. So now we have defined the input and output. Now we have to call this gate. Again we can pass directly like A comma B. A will be mapped to the first variable and B will be mapped to the second variable. Again we are calling this function, right, gate. So we have to call this with a name. Gate, say unit under test. Now we have to pass the value. Say I want to initialize it once. So initial begin n. So A is equal to 1. So this is like some syntax and some basic just briefing the Verilog. Yes. So any doubts? Okay, so another method, like if you want to in the test bench, if you want to change the order, like say G unit under test, this is the variable in the test in the module, and this is the variable in the test bench. So this is another method to pass the inputs to the module. Okay, so if no doubts, then we can end today's session.